All right, let's do this. All right,
Great.
so this is Tim. There's a number of SEC board members here on the line. We'll introduce in a moment, but I just want to say welcome and thank you. SEC is back after hiatus. We'll just get going on this new platform like the rest of the world is. So again, thanks for joining us today. Welcome to SEC's December meeting. Thanks for all the donations for today's meeting. We'll continue to do it on a donation basis for the time being, and then we'll see how things go. Thanks for our sponsors and our members. We've got some of our sponsors here with Community West, Bengal, Toyon, noted on our website here. So we encourage everybody, if you're not familiar with the organization, to take a look at our website, take a look at our sponsors and our regular programs. Again, we're pushing ahead to make this is kind of the beginning of our restart, if you will, and we're looking forward to good programs continuing to 2021. With that, just a quick raise of hands from the board members. If you could just either come off mute and say hi, or just let everybody know that who's here. And as most of you know from our lunch meetings, we try to get our good speakers from our community, and now with the online program, we can maybe cast a wider net. So with that, let's see, a quick note on membership. As usual, try to get letters out. We know that we've been kind of lapsed for the last few months, but looking forward to renewing membership and as we roll out the new programs. So before I turn it over to Yvonne for her to talk about upcoming events and introduce today's speaker, just a couple of rules of the road, and then I'll let Cheryl or Yvonne correct me here. But as usual, we want to keep our mics muted during the presentation. You can use your chat for questions or raise your hand. We'll keep track of the questions and comments as they come up, and then it's really up to the speaker, but we'll likely, Yvonne will be facilitating those questions after the talk, or if the speaker prefers, we can kind of pause as we go along. Okay, with that, I'm going to go ahead and turn it over to you, Yvonne. If you could please do what you do so well, maybe talk about some upcoming programs, and then kick off today's discussion.
Great, thanks, Tim. I just wanted to give people a heads up about upcoming meetings. We're back in the swing of things, even though we're on Zoom. Our next meeting will be January 13th. And I've sent out invitations to speakers, and we'll have the speaker and the topic for that meeting announced by email soon. On February 10th, we do know that our speaker will be Dr. David Lee. He's a professor in UCSB's Earth Science Department and an affiliate faculty in the Bread School of Environmental Science and Management. He's going to be speaking on decarbonizing California's transportation sector. He's been participating as a member of a statewide panel on CO2 mitigation, and he'll be speaking about the report generated by that panel. And today we're happy to have as our speaker Dr. Mahdi Abu Omar. He's a professor in both the departments of chemistry and biochemistry and the chemical engineering department at UCSB, and he holds the title of Mellencamp Professor of Green Chemistry. He has authored or co-authored nearly 200 peer-reviewed research articles, supervised over 40 PhD students, and has held faculty appointments at Purdue and UCLA. He's a fellow of the AAAS and was a senior Fulbright fellow at the Weizmann Institute. Dr. Abu Omar is the founder of Sparrow Renewables, a clean tech company that provides cost-effective and renewable substitutes to petrochemicals. And we are pleased to have him speaking today on creating value from plastic waste. If you have questions during today's talk, you can type them into the Zoom chat area or ask them after the talk when we'll allow you to unmute yourselves. Thanks. Dr. Abu Omar, go ahead.
Okay, great. Thank you, Yvonne, for this invitation, and Mary for allowing me to speak to this group. Normally, what I like to do is tell people that they can interrupt me and ask questions as we go along, but it seems like with the Zoom format, maybe this is a little bit more difficult. Do interrupt me if you feel that a question is more appropriate than waiting till the end. I'm happy to answer the question. Okay, you see my slides, right? So I want to tell you today about creating value from plastic waste. And there's no question that plastics have changed our lives. There's not a single aspect of modern life that does not involve plastics. And it's not all bad. The use of plastics, lighter weights in cars has saved energy. I guess your next speaker is going to talk about how we all going to be driving electric cars in California by 2200 or something. I'll be dead by then. It wouldn't matter. My children enjoyed a lot of toys that were made out of plastics. They're no longer children, obviously. I continue to enjoy plastic containers, elastomers in shoes, electronics, food storage. The message is obvious. Modern life would not be where it is now without plastics. It would be something else. How did we get from here to here? This is the Arabian Sea. This is a man actually walking on this shore, and this is plastic garbage. This is all plastic garbage. I'm sure I could have picked another picture, but I thought this is Mumbai, India, and this is a famous bridge, and this is the Arabian Sea, and I'm an Arab, so this is appropriate, and this is a lot of plastic garbage. So how do we go from this amazing stuff to something that really bothers a lot of people and is becoming a serious problem? And the reason is this exponential growth in plastic. So in 1980, and I picked 1980 because I think it's an important year, I was 10 years old, and that's maybe when I started paying attention to science. I don't think that's true. But here's 1980, we were making every year 60 million tons of plastics. And exponential growth starts happening. And by 2017, and I'll explain why 2017 is a special year, and that's where my statistics ended. But, you know, 2020, we're going to be probably close to 400 million metric tons per year in plastic. So from 1980 to now, the amount of plastics we produce every year has gone up by a factor of 6. Notice that these bars are related by a factor of 10 because we scientists love factors of 10. So obviously we make much more steel. This is how much steel we were making in 1980, 600 million metric tons. And now in 2017, we made only 1,700 million metric tons of steel. So as you see, steel has increased by a factor of 3, while plastics have increased by a factor of 6. Why 2017 is an important year? That's because when our colleague Roland Geyer has published a paper in Science Advances, so Roland is in Bren, and he has published a paper that is attracting and continues to attract a lot of attention. And he basically put on a figure the total amount of plastic waste. And based on his calculations, he predicts we're going to be in waste up here by 2050. And that's probably before we all go electric in California, which, by the way, as we go electric, well, unless all of you want to drive Teslas, but anyway, as we go electric, we're probably going to be using more and more plastic in those cars because lighter weight is going to be more and more important, and the lithium is going to be the next petroleum, and that becomes a topic for a different talk. But anyway, as we go electric, we're going to probably continue this growth in plastics. But what Roland really opened our eyes to is this is the total garbage because it's going to keep accumulating. And this is where we are now in recycling and burning. So it's pretty pathetic. We're down here. We're not recycling anything. And I'm going to explain that also, why we're not recycling anything. And he's actually very optimistic. So he says if we really increase exponentially in burning our plastic, which by the way is not good for carbon unless you capture the carbon, and if we increase tremendously in a very optimistic way in how we recycle, the total of both of these is still pretty small compared to how much garbage is going to accumulate. So I'm not going to put words in Roland's mouth, but I want to tell you that what these graphs tell us is we think we are in a disaster here, and we are not in a very happy situation. we're heading towards worse and worse situations unless we figure out how to solve this problem. And I don't think it's going to be a one type solution. And of course, I'm going to be biased in this presentation to my own work, but I'll try to be balanced by reminding you that this is one of these things where you're going to have multiple solutions. Otherwise, even with optimism with recycling and burning the waste plastic for heat value or for energy, we're still heading to trouble because we can't keep up with the pace of how much plastic waste we are producing every single year that continues to accumulate. So one of my former graduate students, these numbers are very big, 350 million metric tons per year of plastic. How do you make sense of these big numbers? It's like I always joke with my students, you know, how do you make sense of our national deficit, you know, when it's, or our national debt when it's trillions of dollars, you know, we can't get our head around numbers that big. So one of my former graduate students, TG, Delina, he's now a scientist at PNNL, wanted to put this number into a visualization. So he came up with a number for the density of the Empire State Building. And he called this, I should have put this in the title, The Empire Strikes Back. And every single year, we make enough plastic to build to scale 300 Empire State Buildings that are entirely filled with plastic. So the actual Empire State Building is made out of plastic, and its all volume content is filled out of plastic. Multiply that by 300, that's how much plastic we make every single year. Now, one of our other graduate students here at UCSB in Susanna Scott's lab, and Susanna's name will come up again, took these numbers from Thelina, and he actually realized that we could build multiple times every year the Great Wall of China with the plastic that we make every single year. That's just to give you a visualization of these millions of metric ton numbers, because it becomes very easy for us to talk about big numbers, but how do we put them in context and think about them? So what are these plastics? It turns out that the king of all plastics is polyethylene, or what you see as PE. So that's more than half of the plastics we make. And then a big portion is polypropylene. And then PET are the plastic bottles that we use in beverages, in water and so forth. So as you see, PET, even though it's very significant, is very small compared to polypropylene and polyethylene. And of course, well, all of these plastics come from petroleum, but polyethylene and polypropylene, as you see in a second, are basically very large chain of hydrocarbon. They're impressive. If you want to think about it, they're just really long chain of gasoline of some sort that makes very interesting materials that we use all the way from the cover of this Starbucks that actually is labeled number 5, and it says PP. So the cover of the Starbucks or any coffee that you drink or you buy is polypropylene. So when we got into this, we realized that to really make a significant dent in this, you have to really consider how do you make value out of the waste that is polyethylene and polypropylene. I mentioned that recycling is not going to save us. I don't want you to get disappointed with me. I hope I convince you today why recycling is not going to save us, because we don't have the technology to recycle plastics. You and I and everyone on the face of this planet, we were lied to that you could recycle plastic. So this is again from Roland's paper, a beautiful figure that shows how much plastics are going in, how much are coming out, how much are ending up being burned, and how much is really recycled. And that 7% is pretty optimistic. So really, we're not making a dent by recycling, because we're only recycling about 7% at the most of the plastics. And part of the problem is We have technology and we know how to mechanically recycle, for example, polyesters, such as the plastic bottles, PET, and that always gets downcycled. The recycled material goes into carpets and other things, does not really close the loop and make a bottle, but we know how to recycle this. We know how to recycle some of this. We don't know how to recycle most of this, all of this, we don't know how to recycle. So we are not recycling, not because you and I are bad citizens and are not putting our plastic into recycling bins. It is because the industry basically manufactured recycling without really having the technology to recycle, nor having the intention to spend the money to develop the technology to recycle. It was simply shifting the responsibility to the consumer. Hey, it's your fault. We put a number on this thing and we put a little circle. That means it can be recycled. If it doesn't get recycled, it's Mary's fault, it's Kevin's fault, it's Mari's fault, it's Tim's fault. It's not my fault as a company that I'm making this great product that you're enjoying. And there's two articles. Oh, I guess I forgot the New York Times article, but I can send you the reference. There's a New York Times article that covers this pretty well. There's a fantastic frontline PBS program that came out, unfortunately, during the pandemic, but came out in March 2020 about plastic wars. And some of the individuals they interviewed that really confessed to this were the leaders in creating the whole recycling system. And in fact, they were the heads of these societies that the industry made as the Society for of the Plastics Industry, that really claimed that this is a solved problem. We just have to get people to recycle the stuff into the right blue bins and everything is going to be sold. And that was an absolute lie. Of course, I'm being very strong about this statement, but if you watch Plastic Wars, you will see where it's coming from. And the message keeps shifting, okay? So we invented these numbers in the 70s, and then in the 80s, it was all the amazing things you can do with plastics. And then responsible people like you and I started thinking, well, wait a second, we got to make sure that we can recycle these things. And the message shifted in the 90s and in the 2000s to you are just not recycling enough. Keep recycling, keep collecting, keep having days on the beach of collecting plastic and sorting plastic. And in fact, very recently, the industry put together something called Alliance to End Plastic Waste. It's actually all the same people, the same funders that have funded the same organizations back from the 70s to tell you, you're just not recycling enough. So why these things persist? Well, these things persist because they are made out of hydrocarbons. They're made out of carbon and hydrogen bonds that are not very reactive, and the environment doesn't know how to decompose them, okay? So we published a paper recently, and we involved Susanna Scott here and some of our students, as well as Sangwan Su, another colleague of mine at Bren. And we really looked at plastics and how they degrade in different environments, under the sun, in the land, in marine environment, in seawater, depending on what kind of plastics they are. You know, here is the whole hoax with the circle that this thing is really being recycled with numbers to sort them and all these things that actually don't make a dent in the plastic waste. And some of these things take tens of years, hundreds of years, and even thousands of years to degrade under different environments. And to give you an idea, this is high density polyethylene. This is the milk jug at your home, which actually we know how to recycle high density polyethylene mechanically, except that the milk jug is an exception of high density polyethylene that's pretty pure. So what happens in most of these plastics is they are really a mixture where you have films of different components. And we looked at how these things degrade based on fiber versus film versus bead. And there's no question, and we developed this simple equation to predict their degradation rate, if you will. There's no question that very thin films will degrade in few years much better than fiber, and fiber will degrade better than beads. And you get the idea that with bulky things, it's going to take thousands of years for these things to degrade in the environment. And that's why the beach picture that I showed you is very striking. When these things leak in the environment, they're going to hang around for a really long time. I know I was told don't get very technical, but for those of you that know chemistry and know molecules can enjoy this slide. For those of you that don't, I'll try to walk you through it. As I mentioned, polyethylene and polypropylene are basically carbon stitched together in very long chains. There's nothing else on it. And the way it degrades in the sun by UV or by oxidation is it makes other organic oxidized molecules. Some of them can degrade further. Some of them are pretty toxic that won't degrade further and may be more harmful than what you started out with. But this is the process that takes a really long time. And when you compare that with something like PLA, polylactic acid, that's made out of a bio-based material, that actually degrades to the monomer, which is the component that this long chain polymer was made out of. And these are pretty compatible with the environment. You could degrade faster, but you degrade to materials that the environment knows what to do with it. So how can we solve this problem? There are multiple ways. I'm not against continuing to improve mechanical recycling and downcycling. That's important. But I think from the data that we have, that's going to improve things in a very small way. The other two avenues that I think are going to be very significant is how do we make plastics that are compatible with the environment, that we either figure out ways to collect them and recycle them, or if they escape into the environment because of human behavior, because we sell our garbage to Indonesia and China. And by the way, China stopped accepting our plastic garbage. They're going to be compatible with the environment. That's one approach. Another approach is we continue to use these polyolefins from petroleum. Can we figure out some new chemistry in which we could return them to the components that they're made from and close the cycle completely, or use them as a feedstock to make other things from them so they are not waste? They are not really truly garbage, making value out of that waste, because that's good for the economy and that's also good for the environment. What I'm going to tell you about today is our recent work on what is called in the literature now upcycling, making value or making higher value from polyolefin waste, specifically polyethylene. But I'm going to take a little diversion and a little break here and just give you a couple of slides about Sparrow Renewables, a company that I founded that actually develops bio-based plastics, particularly for composites and high-end materials, to enable recycling of high-end materials. Well, I had one slide before that. I forgot my order. I apologize. So today, the way we do things is what's called a linear economy. We dig a hole in the ground, we get some stuff, we make interesting materials from it, it becomes garbage. We dispose of it, we burn some of it leaks into the environment, but it's totally linear. At the end of the lifespan of the bottle, the shoe, whatever it is, that plastic all becomes garbage and we start all over again. We mine, we make, we use, we dispose. A very linear economy. The future and the idea behind Sparrow Renewables is how do you make things circular? The future is going to be a circular economy. We make things from monomers or from building blocks that are compatible with nature, that come from nature. We could make sophisticated materials, use them, and build in these materials recyclability. I think that's a point I want to stress, actually, I don't want to miss. The plastics we use today were not designed to be recycled. Were not designed to be recycled. That's something I think that the industry now is really fessing up to. They understand that this whole recycling and numbers they invented was hoax because they didn't really have the technology to do the recycling. So I want to show you just one example from Sparrow where we use wood-based polymers actually to make composites like this carbon fiber composite that's completely recyclable. And this is just showing you a prototype demonstrated with a skateboard. These are the same carbon fiber composites that we are making today from petroleum, and we're using in cars to save energy and be able to get more mileage out of the car. But the idea here is to have material that enables recyclability. The chemistry for recycling back to the components that this is made out of is built into the design versus all the petroleum plastics that we use today that don't have recyclability built into them. But what I want to tell you about today is actually work that we've done on polyethylene specifically. And that is more than 50% of the plastics that we use. It's in food packaging, in all the materials basically that we end up using one time for a very short time and throwing it away. And there is no technology today that can mechanically recycle polyethylene. And the reason for that is polyethylene are these CH2 units, carbon with two hydrogens on it that are stitched together in very long chains. Makes fantastic materials, but terrible to recycle, chemically very inert. So it's actually very challenging to make from it other compounds or return it back to the starting materials that it's made from. I want to remind you, and you know, we scientists are really good people. We always are very honest. We're trained as scientists to be critical of our own work. So even when we do good work, we're critical of our own work. So I want to remind you that we could always pyrolyze this the same way that we can pyrolyze wood, we can pyrolyze petroleum itself and get energy out of that pyrolysis. But I want to tell you that that's sort of the last ditch effort, that we just take all that waste that we spent a lot of energy to harness and end up basically burning that product. So, but I want to remind you that if we just wanted to pyrolyze all that plastic waste, we could do it, and we could do it today. And in fact, a lot of chemical companies, I won't name names, that will tell you, whatever, Professor Abu Umar, Professor Scott, all those people are crazy. They want to do something too ambitious. The only way to deal with these plastics is to pyrolyze them. And when the government requires us to get rid of that waste and they put a price on carbon, we will just pyrolyze everything. So I just wanted to keep that in your mind. Before I tell you about the science, I have to really acknowledge the true people behind this work. This has been a team effort entirely between my colleague in chemistry and chemical engineering, Susanna Scott, and some of her students. Both Jackie and Fawn are in her group. Danny and Ariel are graduate students in my research group. We collaborated with Baron Peters, a defector from UC Santa Barbara. He's a chemical engineer that moved recently to the University of Illinois, and his student Ryan. These guys did a lot of the modeling work. I probably won't tell you a lot about that. And Dr. Anne Lapointe is a scientist at Cornell that helped us with a lot of the polymer analyses. But this is the team that was on the science paper that appeared recently, and that's what I'm going to be telling you about, is what can you do with polyethylene? And This is pretty technical, but I think I can walk you through this. We take polyethylene, the polymer, and in this picture, I'm showing you, actually, I'm cheating here because I'm showing you clean polymer. And remember, I told you one of the challenges is even that cap is pretty clean polyethylene. It often has a film of something else on top of it. So any plastic that we deal with today is a mixture of different plastics. And that's an important thing, even when the major component is polyethylene. But here in the reactor, we put polyethylene, we put this platinum catalyst. This is some platinum particles on an alumina solid. And we heated this up to 280 degrees C. So those of you that are not used to Celsius will say, what the heck is 280 C? That's about 550 Fahrenheit. So that's not terrible. I think you're gonna bake most things in your oven at 400 or 450 Fahrenheit. But this is a very slow reaction because we melt the polymer, we melt the plastic, and it slowly interacts with the catalyst. And at the end of 24 hours, this is a whole day. And by the way, I'll tell you that we improved this to hours now, so we could do this reaction in 4 hours. You open this reactor, and this is the product that you see. You see a liquid. We turned this, and this liquid is after we filtered the solid catalyst out. You get 3 components. You get the solid catalyst with some remaining hydrocarbon plastics with it. You get small amount of volatile gases. And the major product, it depends on the plastic, 70 to 80% of the plastic is this liquid. Okay? So this was very exciting for us because, you know, you're starting with a solid, you do this reaction, we're not using any solvents. We are using an expensive metal, okay? So we're using platinum, but I want to remind you that each one of you, well, those of you that drive Teslas, you don't have such a thing, but there are some other problems with Tesla. But those of you that drive gasoline cars or diesel cars or whatever, have a catalytic converter in your car. And the catalytic converter in your car has in it a precious metal. So we know how to recycle this platinum completely. So we recover this platinum here in the solid, and we have a liquid product that comes from this reaction. When we analyze this liquid product, let me tell you that the gases that we make here are typical hydrocarbon gases. We make a little bit of hydrogen, we make methane, ethane, and propane. These are the main components. These are a small percentage overall, but I'll come back to them later. These are actually important because we can use them to heat our reaction, okay? So we can use them in the whole process so that we can be self-sufficient, not using carbon from outside sources to enable our chemistry. If we run this reaction without a catalyst, this is experiment 0. If we run this reaction without a catalyst, we make some liquid, but very small amount. But that liquid actually is not as clean as what we make with a catalyst. And the majority of our product is crud, is basically the polymer getting to be more difficult to work with. This is showing you experiments with different low molecular weight polyethylene. Those are the clean experiments. And that's where I told you we get 70 to 80% of the material into this liquid product. But we did real samples. We did real life plastics because we figured that would help us to get the publication in Science. So if you want to read our publication, this is the reference. I'm happy to share it with you if you want to look at it. And the students, of course, got excited. They got really excited. They wanted to do real samples. So we did a plastic bag, probably not this specific plastic bag, but we did a plastic bag. And we did high density polyethylene that's reasonably pure, your milk jug. We actually took the cover of the milk jug and grinded it and did the experiment with it. So notice the plastic bag performed pretty well. It's comparable to what we did with the clean stuff. there was a little bit, oops, sorry about that. There was a little bit more solid there, and that's because you've got some dye, some other components there. The high density polyethylene did not do as well. So I want to show you this real life comparison. We still got very modest but good yields of this liquid. What was really fantastic about this discovery, and I don't know how else to communicate it to you without getting too excited about the molecules and the chemistry, is that that liquid product that we made was not just hydrocarbon, was not just breaking up this big polymer chain into smaller chains that we could use as gasoline or as diesel or as jet fuel. It was actually fancy enough chemistry that we were making specifically these cyclized molecules with long hydrocarbon chains that are exactly the same molecules. We were making these type of molecules. They were exactly the same molecules that are called LAB, linear alkyl benzenes, which we make from petroleum today and sulfonate them to make all our detergents. So a huge percentage of all the detergents that we use contain what is called LAS, and LAS is linear alkyl sulfonates that are made from LAB, that are made from these molecules. We are making these molecules from waste plastic, from waste polyethylene. And at the beginning, that actually went against chemical convention, because in the chemical industry, these molecules are made at very high temperatures, and we were making these from waste plastics at lower temperatures. So there was an energetic consideration that was going against our education as chemists. So those of you who are chemists or chemical engineers, we actually thought we had a problem in thermodynamics. This cannot be thermodynamically possible that we could make this. And it turned out the reason we were successful in making this, because the price for making this, we were paying it energetically by breaking these very long chains in the plastics. So they could not do the same chemistry from petroleum, because petroleum did not have these long chains like the plastics do, where we can compensate for our energy by breaking up those chains. So the story became very, very appealing. We're taking waste plastic and we're making from it high value molecules that we actually make today from petroleum by energetically more demanding pathways. So this next slide is super technical, and I think that some of the chemists in the audience maybe will appreciate it. Everything in chemistry we do today in the chemical industry comes from naphtha. And naphtha basically is these petroleum molecules that we actually crack in a big cracker at very high temperature at 1,000 degrees Celsius. And then from these molecules, we build everything that we use. So these detergents are made by taking this naphtha with a rhenium platinum catalyst at 600 degrees Celsius usually to make these materials. We call these materials benzene, toluene, xylene, BTXs. And from these, we actually combine other gasoline-like molecules to make these lab molecules that go into detergents. We sulfonate these and they go into detergents. And because of the sulfonation, they are biodegradable. So they go into the detergents, we use the detergents biodegrade. The UCSB process now does this in one step. Sorry about that. The UCSB process does this now in one step. We start with the waste plastic, and in one step, we make these materials. So this became, once we can answer the science question of why we were successful making these materials from waste plastics, that immediately became apparent to us. We have a science paper. And I think that sort of, I always believe that it's better to be lucky than to be smart. But I think, 90% of science is doing the experiment and getting something you don't expect. And this is certainly the case. We did probably an experiment that 90% of us on the team were thinking that's the craziest experiment under the sun. We're gonna mix two solids, heat them up, and we're gonna expect to get an interesting result. And we actually did. And when we got a result and we were very sure of it, we started talking to our colleagues around the world, and the majority of them said, you have a thermodynamic problem. You have an energy problem. This is impossible. But we knew we were making this product, so it became a challenge for us to understand why what looks impossible was actually possible. And it turns out that there is a scientific explanation for it, and we cracked it, and it allowed us to have a science paper. So we published the science paper, and science does something very nice when there is an interesting discovery like this. They go find an expert in the field. They found this guy, Bert, from the Netherlands, another colleague, and they asked him to write a perspective and explain in few paragraphs what remains to be done and why this work is important. And I like to show this perspective because it talks about the importance of art. So actually, Bert, I don't know if it was Bert or the science folks, they came up with a better drawing of our process than what Susanna and I came up with. So I thought that was very interesting and they hide this from us. They don't show it to us until it's published. So this is the plastic molecule, and this is actually the platinum catalyst on the alumina surface. And alumina and alumina silicates are basically glass. I want you to think of this as sand material, okay? So these things go together here, you heat them up, and you make these molecules that end up being the molecules that we know how to make detergents from. So Bert wrote a very nice perspective, and now I like to use the picture that he came up with, or science came up with, as our process. Now you might be asking yourself, well, okay, you did this in the lab and you did this on a small scale. Can this scale? And this is really one of the challenges, and this is what we're working on now with Susanna and others here at UCSB and elsewhere, is how do we scale this process, and does it have economic legs? So this is just a very primitive thinking of the process itself. You're feeding in a plastic, and I did this calculation, back of the envelope calculation based on cost. What is it going to cost you to get this plastic waste, move it around for a certain distance, okay? And we're going to spend some energy to do this reaction. Then we're going to spend some money to separate the catalyst back and to separate some of these gaseous molecules that we're going to use for heat. And then we're going to get these alkyl aromatics, which are the lab molecules that we make detergents from. And as you see, we're going to have maybe $5 cost per ton. We maybe have people pay us to collect the garbage, because it turns out that you and I apparently pay companies to collect garbage from us and to collect plastic from us. And we always feel good that we're recycling that plastic. But anyway, I know that always economists are suspicious when scientists say somebody's going to pay me to collect this garbage, because business people by nature are not as nice as scientists. When they discover somebody is making money out of their garbage, the garbage becomes valuable. They're going to charge you money for that garbage. But I just want to show you that this could be maybe on the $5 cost. I have to spend money doing all this processing, but my product is on the order of $1,000 per ton in value. And that's pretty conservative. So I have room to play with the cost here. There's no question that when you start building a process like this, the capital cost is going to be intensive, particularly the first time that you do this. And no question about it, we have to get chemical companies and petroleum companies engaged, and we have to get them committed to something like this. The good news is a lot of the chemical companies we're talking to now realize and understand that there is no way of escaping that problem. They cannot keep telling you and I there is a number on this thing and you are just not recycling enough, because that is not true. So I want to end here by saying, I hope I introduce you to a new way of thinking, a road that is less traveled. And that road really, if I were to sum it up in few words, is we always find a hole and we dig and we find a resource like petroleum, and we always mine below the ground. I want you to think about this plastic problem as a feedstock and an opportunity to mine above the ground and to really help humanity move forward in a positive way, but make economic value out of this waste feedstock that if is left in our environment or in our landfills, it's going to take hundreds to thousands of years to degrade. I thank you for your attention, and I'm happy to answer any of your questions.
Great, thank you so much. We had a couple of questions in the chat, and then we'll let people unmute themselves and ask questions. Maybe just wave at us first so we don't have too many people talking at once. Someone asked, does most of plastics really degrade, or do they become microplastics?
I didn't want to open that can of worms. You probably should talk to Tricia Holden in Bren, one of my colleagues at Bren. Well, given enough time, you will go to the molecules, and that chemical scheme I showed you is real. But there's no question, in the way to these molecules, you first make a lot of microplastics, particularly from thin material, thin film, small chunks of plastic, etc. And the microplastics is a whole other beast. Because the implications there and the environmental problems in the ocean and getting into our food, into the fish and your food and my food. So, you know, in science, we tend to specialize. So that's a well-recognized issue.
And was it a lie when we were told about maybe 10 years ago or something that plastic films were recyclable, or were they recyclable at some point, but nobody's taking them?
So the majority of plastic films are polyethylene. They're very complex materials, actually. The majority is polyethylene, but then there's, of course, the gas barrier materials like EVOH, the ethyl vinyl alcohol that gets put on top of the polyethylene. Food packaging, plastic films are not recyclable. We do not have the technology to recycle them. Please stop putting these in your blue bins. In the sorting, if you visit one of these places where they sort plastics, they will show you and tell you how much of a headache these plastic films are, because they clog up the belts and the sorting apparatus and stuff like that. We don't have a technology for recycling them. They are not recyclable. When I learned, 2 years ago, 3 years ago, so this paper that I referenced, where we calculated, and this is, we just published that paper, by the way, 8 months ago in American Chemical Society Sustainable Chemistry and Engineering Journal, and it has been getting a lot of attention. We looked at different plastics in different environments under sunlight versus aquatic environment. And the sad part about all of this is there are so many things. Everything that you buy is labeled with a number and a circle. And the majority, 90% of those things cannot be recycled. The one that we do a good job with is PET, which is polyester. And water bottles, Coke bottles, those are PET. Once you remove the bottle cap and once you remove the label, they are mechanically recyclable, downcycled. Downcycled means they don't go back to a bottle. They go back to a lower quality material that ends up in a rug, that ends up maybe in a shoe, but at least is recyclable to a second life cycle.
Okay. Do other people have questions that they'd like to ask?
Yeah, this is Matt Dunn. I have a couple questions. So when you said mechanical recycling before, do you mean what you just said, which was making a coarser material, or are you talking about squeezing them into park benches?
No, making another material, mechanically recycling the plastic into another resin, into okay. A material. Yes. All right.
So the second question I had is, I understand where you're going about beating the petrochemical complexes at their own game of making the intermediate feedstock for our consumer uses. But, you know, geographically, a lot of the petrochem companies are going to be national oil companies. So when Sinopec wants to have more benzene, they're just, you know, they're just going to release a contract for some BTEX plant. Mm-hmm. And they're not subject to the investor pressures that, you know, private companies are. So that's just, I guess that's just an observation as opposed to a question. But.
Matt, correct. The complexity that you've presented is there. Right. In the chat, Wilson has a question about the platinum catalyst and whether there is a coking problem. A coking problem means you get carbon deposited on the platinum and it becomes less active. An excellent question. It is indeed one of the things that we have to improve in the process. In the science paper, we demonstrated good recyclability of the catalyst. But as I noted that there is what I had colored black, the solid material that's left over, it's a decent percentage of the starting plastic. It's in the few percent. And the only way that we were able to recycle our catalyst is by regenerating the catalyst under reducing environment. So that's definitely going to be an important consideration, not for the laboratory scale as much as for the practical scale, but that's definitely an improvement that we're working on. I think we've demonstrated that it is doable even in our early report in that science paper.
Great. Kevin, did you have a question?
Well, I had two questions. One was that one, and the second that Cliff has just asked, sorting. How clean does your input stream? Sorry, how much does it complicate things if your input stream is not pure?
So when we discovered this chemistry, that's definitely something that I have to answer to the best of my knowledge. I showed you an actual plastic bag that we ran. So I think we're gonna be tolerant. The fact that we could handle polyethylene, we can handle mixtures of polyethylene and polypropylene. We can handle plastic packaging that has some other materials that have small oxygen components in the material. We haven't done the experiments, but I don't think we can handle plastics that have PVC, for example, because PVC is polyvinyl chloride, and that's going to have a chloride that under our conditions is probably, we anticipate, is going to poison the catalyst. So again, our objective is to minimize sorting. We don't want to do this with really pure, clean polyethylene. We want to do it with mixtures, and we're very encouraged that we can do this with polyolefin mixtures and other mixtures. There will be limitations. One of the limitations we're aware of is things that have in them PVC. There might be some dye components that become really damaging for our process. This is one of those things that you have to test. It's one of those practical questions. But as far as sorting the mixtures, there's a lot of things that are mixtures of polyethylene and polypropylene, mixtures of polyethylene and vinyl alcohol. And I think those kind of mixtures we don't have to sort, and we don't have to worry about the problem of sorting.
Right. What about food contamination? Is it possible that could be baked off or separated from the liquid?
Yeah, that's a good question. I think food contamination, you're probably gonna have, just like any process that handles a feedstock, let's say a dirty feedstock, you maybe have to have some pre-processing, some mechanical washing, some soaking, some steam washing. This gets into the engineering realm. I think given your questions, guys, I think some of the people in the audience here probably know that our petrochemical industry is sophisticated enough. I mentioned that petroleum goes to a cracker and naphtha is made from that. And then all the chemicals and materials we use are made from naphtha. The petroleum industry is sophisticated enough now that not all crude is treated the same. So a crude that comes from Saudi Arabia versus a crude that comes from North Dakota, they do certain analyses on it and say, okay, we need to turn this lever, change the temperature, change some pre-treatment this way or that way. And I think this would have to be part of the process dealing with the plastic as a feedstock, especially, mixed plastics, contaminated plastic, etc. Mary had a question.
Well, I think you've sort of answered it. I was just going to ask if some of the dyes could not be leached from the starting materials through processing in the beginning, doing after the sorting is done, do leaching and things of that nature. So we all know that in real life, you've got to do that processing prior to getting to the plant. And this is, of course, going to add to the cost.
Right.
People aren't going to pay you to do that one.
Right.
There's a couple of questions in the chat about scaling up and then the amount of polyethylene that could conceivably be upcycled and versus the current detergent market.
Okay, excellent question. I think we discussed a lot of the technological challenges, some of the chemistry, some of the engineering challenges that we have to deal with as we scale up. I believe that big component of scaling up, and this is coming soon, is going to have to be identifying the feedstock. In other words, identifying a feedstock that would be a good candidate for this process. And in the chemical industry, at least for something like this, we do the scaling in a stepwise fashion. I mean, we're already thinking about how do we do this, let's say, on multiple kilogram scale. That, of course, is very modest scale up. After that, you would think about what we call in chemistry piloting. You would pilot this on a ton scale before you really go to the hundreds and thousands of ton scale that you're going to operate on that's going to be profitable. Obviously, if we consider the total amount of polyethylene produced annually versus the detergent market, there is a mismatch. I have to tell you that right away. So that question from Stephen is a very good question, okay? If I'm gonna recycle all of the polyethylene, I'm gonna make probably more of these, you know, pre-detergent molecules for that higher end detergent application. But what I want to point out to you is we're making molecules, and given that these molecules can go back to something that is the same as BTX, we practice that chemistry at the scale of plastics and more. So while the detergent application, so I like to think of this actually in our own process, I like to think of this as the two levers that would have to be turned to make the economics versus scale right. The first plant that you build and you make this product, you probably don't make enough to make a dent in the detergent industry, and therefore you could get the higher value. As the process becomes proven and can scale to more and more waste polyethylene, I think we can, you know, we can start thinking about using these molecules for lower value feedstock that makes also plastics, that makes the starting plastic that will match the scale. And I think the economics can work out. It will be a process. We won't go from the first plant that's maybe going to handle, you know, thousands of metric ton to millions of metric ton, thinking that it's the same product, it's going to make detergents at this higher end value. And that's, and you know, that's something that we deal with in the chemical industry every day, scale versus value.
Great. Let's see, there was also a question asking what the next step for commercializing for either your lab or your company might be.
So these are two different pathways. So the next path for commercializing the polyethylene upcycling is exactly what I told you, is actually demonstrating the process and getting numbers on it by running the process continuously on larger than a lab scale, but not a huge scale, so that we can get all the engineering questions in place. What type of reactors we're going to use, how robust is the catalyst, etc. That will give us all the techno-economics that we would need for commercialization. We're doing something very similar with the materials that we're making that are bio-based for making composites at Sparrow Renewables in the company, and we've already demonstrated that on kilogram scale and beyond, and we're actually trying to find good companies to partner with. I mean, we've been talking to a few different companies, including even Patagonia, about you know, doing prototyping and taking to market our bio-based recyclable product. So now we're sort of in the stage of trying to find product outlets for that, for those materials and that chemistry.
Great. Other questions from anyone? Well, we want to thank you so much for your talk, and we really appreciate it. So
Thanks for having me.
Thanks.
I appreciate it too. Bye.
bye.